It's my great pleasure to introduce Professor Pieter Abbeel, who is the director of the Berkeley Robot Learning Lab and co-director of the Berkeley Artificial Intelligence Lab. Professor Abbeel's research strives to build ever more intelligent systems with main emphasis on deep reinforcement learning and meta-learning. His lab also investigates how AI could advance other science and engineering disciplines. He has founded several companies, including Gradescope. This is an AI to help teachers with grading homeworks and exams. And recently, Covariant, which is an AI for robotic automation of warehouses and factories. He has received many awards and honors, including the PCASE NSF Carrier, ONR YIP, DARPA, TR35, etc. His work is frequently featured in the press, including New York Times, Wall Street Journal, BBC, Rolling Stone, Wired, and Tech Review, and he has several influential papers in the field of reinforcement learning. And today he's going to be telling us about unsupervised reinforcement learning. So Pieter, the floor is yours.
Hi, Mazir. Thanks for the introduction. Thanks everyone for joining us here. Actually, I thought I'd first share an interesting anecdote. As I was talking with Mazir, I have actually not yet spent a night in Colorado, but I grew up in Belgium, and the first textbook that I ran across in my undergrad in Leuven, which was on, I believe, object-oriented programming in Java, was actually by Michael Mann from University of Colorado. So the first US university I had a textbook from was the University of Colorado. So that's that, and it was a great book. It was nice. So what I thought I'd talk about today is unsupervised reinforcement, which will be the main topic, but I'm also going to cover a couple of adjacent things. So I'll start with talking a bit about neural net architectures and some new work we've done there that I'm pretty excited about. Then the next two sections will be about two aspects of unsupervised reinforcement learning, which is about trial and error learning, but without reward supervision or with minimal reward supervision. So agent should learn on its own as much as possible. But then at the end, I also want to wrap it up with looking at what if we want to bring a human into the reinforcement learning process to give feedback during the learning, how to do that maximally effectively. Now, when we think about a lot of progress in AI in the last 10 years, a big driving factor has been, of course, more data and more compute to train on that data. And it's led to breakthroughs in image recognition, language processing, and so forth. But a big part of it also has been thinking through neural net architectures that can absorb that data in an efficient way that generalizes and then can do well on test data or test tasks in the future. And so one of the models that have maybe, at least for me, was most strikingly capable was when OpenAl released its model GPT-2, which is a language model. And this language model was trained on a lot of text downloaded from the internet to predict the next token in a document. And after training for a very long time on next token prediction, you could then use it and present it with a prompt and ask it to predict the next token. And after that, the next token, and repeat to complete the document. And so here's an example of a prompt. A train carriage containing controlled nuclear materials was stolen in Cincinnati today. Its whereabouts are unknown. Okay, now this is the prompt, and then you can ask GPT-2 to complete this, and this is what it came up with. The incident occurred on the downtown train line, which runs from Covington and Ashland stations. In an email to Ohio news outlets, the US Department of Energy said it's working with the Federal Railroad Administration to find the thief. And a quote from the US Energy Secretary and so forth. And so when you read this, it feels like a real news article. It's actually not necessarily grounded in what happened in the real world. And you need to do some fact checking, and in this case, it would not be true, but it reads like something that could be true, showcasing that it's really understood how articles tend to look when you go and read articles on the internet. Of course, then, with the release, there was a lot of news about the release of, well, really the non-release of the model behind this, because OpenAI said, well, maybe this model is too powerful because people can generate fake articles so easily, fake content so easily. So maybe we shouldn't release this, and OpenAI then did a gradual release over time, less capable model first to see if they might be abused or not and what the countermeasures can be and so forth. But in all that news cycle about, too dangerous to release because it can generate fake news, what's easy to lose is actually the research under the hood. And some of the results that they showed was that if you look at the wide range of natural language processing tasks, so every row in this table is a different natural language processing task. The details don't matter so much, but these are different tasks that traditionally you might train different models to solve these different tasks. That if you look at the previous record on each individual task, and then you look at GPT-2, our result, by the way, not my result, this is a table from the OpenAI paper, I was not involved, but the GPT-2 result is better than any previous record that was often specific to the task, showing that if you first pre-train on just large corpus of text for next token prediction, and then do a little bit of fine tuning on a specific task, you can outperform a more dedicated effort on that specific task. Similar thing happened around the same time with a model out of Google called BERT. And again, the details of the table don't matter. What matters is that the boldface line, everything is boldface at the bottom, meaning that every entry at the bottom is the strongest entry for that column, showing that for every NLP task evaluated on, this new model BERT, the large version, outperforms previous state of the art. BERT doesn't do next token prediction, it does masked out token prediction. So instead of removing the remainder of the text, you just drop out some words, but the same idea. You just download a lot of text and train a model to fill then in things that you masked out. And you can train very large scale because there's so much text out there. And to train, you just need to mask some things out and ask it to fill back in. So I think this is arguably the biggest trend in AI of the last few years, that these language models are so capable to generalize and that it's become the norm to pre-train on unsupervised data and then fine tune or even just probe for new tasks. Now, personally, I don't work that much on NLP, and what I presented so far, none of it is my work, just to be clear. But I think it is a really important trend. And so the question we asked ourselves is, might these pre-trained transformers is just a type of neural net architecture that's under the hood in GPT-2 and in BERT, might these pre-trained transformers be even more general than people think? Meaning, is it possible, let's say, that we pre-train on language, but what it learns under the hood is a much more general reasoning mechanism, and that can be reused for solving other tasks, maybe solve some mathematical reasoning tasks, or maybe solve image recognition task, even though it's trained on language. And this would get to this notion that maybe there's a general purpose kind of reasoning that happens to predict next token that is more reusable than people have thought before. And so we set out to investigate this. This is a paper that we just put in archive a few weeks ago with Kevin Liu, Aditya Grover, and Igor Mordach. And essentially this premise that pre-trained transformers, meaning trained on language, might act as universal computation engines. So what does this look like? We'll pre-train on a language corpus for next token prediction. In fact, we will not even do it. We download a pre-trained model that was trained by OpenAI, GPT-2 model. And then what does that model look like? The top figure shows this. So the gray in the middle, that is the transformer model that is trained on natural language. It has multi-headed attention, layer norm, then there's a feed forward, multi-layer perceptron effectively. Then again, there's a times L there, so there's many layers. Most of our experiments have 12 of those repeated. But then of course, since it's trained on language, if you want to do a bit memory task or an XOR task or a list operations where you just have essentially an expression you need to evaluate and say what the result would be, or MNIST digit recognition, CFAR image recognition, or a protein task like remote homology detection, it doesn't come in as language. So we have one layer that will be new at the entry of the model, which is just turning whatever input we have with a single linear layer into an embedding that's now processed by the transformer. And then the output, the same thing, because we're trying to predict something different. We're not trying to predict the next token. We're trying to predict whether there's a homology or not between two proteins. So, or as one example. So what that means is that we can think of it as fine tuning or training the linear input layer, linear output layer. And then we also fine tune the layer norm parameters that are living inside a transformer block to get the right normalizations. Overall, this comes down to about 0.1% of the parameters are trained. Everything else stays the same. And that's how we're testing this hypothesis, whether maybe training on natural language results in a general reasoning engine that can be reused. So here are the results. So in each case, there are 3 methods evaluated. In blue is the model I just described. It's a frozen pre-trained transformer with, of course, input and output embeddings and layer norm adjusted, but everything else is frozen. So any interaction between tokens on the input will be frozen, any of those interactive computations. Then the yellow is a full transformer. So you're doing that, but then you're willing to train the transformer itself, which you would hope would do better because you now can train more parameters. And then in gray is a LSTM to show that these are actually hard tasks. If you fully train an LSTM, it doesn't really solve them. So it's not that this is some trivial task where just a linear and linear will get the job done. You actually need something pretty complicated in terms of pattern recognition or reasoning, whatever you want to call it, to get good results. And what you see here is that the frozen pre-trained transformer does as well or almost as well across these tasks as the fully trained transformer, which shows us somehow something quite general has emerged in that block from just training on language, even though it's evaluated then on very different tasks. What's the importance of the pre-training modality? You can say pre-training on language, that's the FPT, frozen pre-trained transformer, row 1. Second row is random. And you see random actually is also surprisingly good, but not as good as pre-training on language. Then bit is pre-trained on a memory task. It's where you get a bunch of bits fed into it, a sequence of 5,000 bits, and then you get a new sequence of 1,000 bits with a few masked out, and you need to fill them back in based on remembering things you've seen in the first 5,000. Pre-training on that is a little bit better than random, but not nearly as good as pre-training on language. And then the vision transformer is pre-trained on visual recognition, which is a little bit better on the vision tasks, CFAR10 and CFAR10 LRA, which is a kind of harder version of CFAR10, but then is a bit worse on the other tasks. Then we also looked at a lot of the work you see in language models. The larger you make them, the better they function. Is the same true for then performance on other tasks, and we see the same thing here for CFAR10 performance of this language model. As you grow from small, medium to large, meaning 12, 24, and 36 layers of these transformer modules, you actually get improved performance. Same is actually true for random. So who knows, maybe you keep growing a longer and longer transformer or deeper and deeper transformer, even random might get to some very interesting performance. Then does the trend hold across other transformer models? GPT-2 is the one we worked with, and we evaluate here on list ops and CFAR10. Then you look at BERT, which does the holdout prediction, does about as well, turns out. T5, which is kind of sometimes a more efficient version of BERT, doesn't do as well for the list ops, but almost as well for the image recognition task. And then the long former, similar to T5, not as good for the list ops, but almost as well for the image recognition task. So this is the kind of first thing I wanted to discuss. And to me, this is probably one of the most surprising results we've run across, at least in my group in the last couple of years, I would say, that it's enough to train on language to actually generalize really well on other input modalities, suggesting that there's some generality to the reasoning patterns that live inside this transformer, which, I mean, we still don't really understand how come it's so general and what's exactly happening. But one way to think of it could be that there is just a set of reasoning patterns that's inside the frozen transformer after training on language models. And there is so many in there that there is enough in there that when you do image recognition, there is something available for you to rely upon to then extract the information you need with your linear layer at the very end that you attach onto this. Now, a lot of my work has been in reinforcement learning. And I think in reinforcement learning, the next big frontier is unsupervised RL, where we try to bring in less and less supervision during the learning. What is reinforcement learning? Just to kind of reset for a moment, because maybe not everybody is familiar. In reinforcement learning, an agent interacts with the environment, and often the agent is a robot, and then we think of the robot and the environment as a thing that together constitute the world, and the agent is more the thinking part of the process. And so the agent chooses an action which gets executed, let's say, by the robot in the environment. Then the environment and robot change state, and there might be a reward associated with that. Let's say you achieve a good outcome, you might get a high positive reward, or if you achieve a bad outcome, you might achieve a negative reward. And so the goal is to optimize the expected sum of rewards. And so to make this concrete, maybe for a video game, reward could be the score in the game. Or for a robot that's supposed to run, it could be distance covered. Now, these to train with reinforcement learning for a long time proved pretty hard, but I would say one of the big breakthroughs was in 2013 when DeepMind showed that it's possible to train deep neural networks, specifically convolutional networks, to learn to play Atari games from their own trial and error. And that's the DQN result cited here as 2013, and then the Nature paper came in 2015. But many results have happened since that further improved these results at many, many other places. It's also been some amazing results for the game of Go, which for the longest time was thought of as something that would take a few more decades at least before there'd be human level computer player or human expert level computer player, but it happened in 2015. And a lot of it was through reinforcement learning. And then in my own lab, what we looked at was, can we have reinforcement learning effectively invent controllers for, let's say, robot locomotion? And that's what we see in action here. So this robot is learning to run. The reward function is staying upright, you get rewarded for, because if you fall over, the episode ends. And the more distance you cover off to the right, the more reward you get. And you see that in this video over, in this case, 640, but it'll keep going till about 2,000 iterations. It keeps improving and ultimately on its own figures out how to run. And so we don't have to put any explicit knowledge about what does it mean to run and what does it mean to have stability to design a controller by hand. The learning figures it out how to adjust the parameters in the neural network to decide what actions to take and then figure out how to run. And then the beauty, of course, you can run the same algorithm on a different robot and it'll learn to run. And this is a four-legged robot here. No changes needed to the program that powers this. Just a neural network is getting trained to now control this robot. You can actually do this for a very wide range of skills. And I would say at this point, this is very, very practical. And if you want to build applications around this, let's say video games or animated movies, it's something you can start using. And instead of keyframing everything, you can rely on physics simulation and reinforcement learning to get your characters to go where they need to go. We've done similar things in the context of robotic manipulation with real robots. So this is BERT, the Berkeley robot for the elimination of tedious tasks. And here it's learning to put the block into the matching opening. It's learning both a vision system and a control system to complete this task. And in about 1 hour of trial and error, it's able to learn this, which is quite fast if you think about it, because it's never done anything else before. It's learning from scratch in 1 hour to do this. Then another result that some of you might have seen is this Rubik's Cube result. This was done at OpenAI, and it was shown that you can actually train a robot hand to reliably manipulate a Rubik's Cube and to solve it. A lot of training required, but after a lot of training, it can solve it. Now, the big question that we're faced with, I would say, in reinforcement learning about a year ago is how about the sample complexity? If you look at how long it takes to train, when we train from direct access to state, which often in a simulator you have direct access to the state of the robot, the state of the environment, training can go so much faster than when learning from visual inputs. But when you think about putting things in the real world, you typically only have visual inputs available. You cannot rely on having ground truth access to an underlying state of the world. And so how can we bridge this gap? And the graphs you see here are one of the state-of-the-art methods, D4PG, and it shows the learning curves, meaning as you go to the right, it means the robot has had more trials in the environment. In this case, all the way on the right, it's 100 million training steps in the environment. And then vertical axis is performance, and higher is better. And in blue, what you see is the learning curve. If the learning system, in this case, the neural network, effectively has access to the state directly. And in green is what you get when it has access to visual input instead of underlying state. And it makes it about a factor 100 less efficient, which in simulation, in this case, was still possible to run, but in the real world might quickly become impractical if you need to run 100 times longer for something, often a lot more costly to do it, and often just simply impractical. So the question we asked ourselves is, can we bridge this gap? Can we somehow get the system to learn as quickly from visual input as from state input? And this question, of course, not a new question. And if some of you maybe attended the NeurIPS December 2016 keynote, the opening keynote of the conference by Jan LeCun, you might remember that he presented this cake, which has since become a bit of a meme for in the machine learning community, and it's called Le Cake now, after Jan's last name. And Jan's story with the cake was as follows. Essentially, Jan said, look, if we think about deep learning today, there are three types of deep learning. There is supervised learning, which is what most often is used to make things work, but of course you need a lot of labeled data. Then there is unsupervised learning or self-supervised learning, depending on who you talk with, roughly the same thing. And then there is reinforcement learning. And if we map this to how much signal we get from each, then there's so much unsupervised data out there. That's the main kind of body of the cake. The supervised data is a lot less supervised data out there. That's the icing on the cake, taking up a lot less volume. And then reinforcement learning relies on this reward signal, somebody effectively saying good job, bad job, which is very sparse. And you don't even know when you did a good job. You just know you have a good outcome. And so that's just the cherry on the cake. And so it's a caricature, of course, but the high level message is that Jan's message, and I much agree with the message, that all you rely upon in reinforcement learning is a sparse reward signal. You don't get much signal, and it's going to take a long time to learn, and it might just be impractical. But there are these other learning methods that can give us a lot more signal, possibly. And so the question becomes, how do we bring these together? So maybe also reinforcement learning can be a lot more efficient, thanks to bringing in some other ideas. Now, in supervised learning, the big breakthroughs that happened in the last 2 years are also in some sense in that space, by complementing supervised learning with unsupervised pre-training, better results have been obtained. We talked about in the context of language already, but the same thing has happened in vision. Contrastive predictive coding, V2, was the first one to show a consistent benefit of pre-training for visual recognition. And then SimClear by Jeff Hinton and MoCo by Kaming He and collaborators showed that unsupervised pre-training can truly help image recognition. And these are just about a year old, these results. Now, we started looking at, can we apply the same ideas in reinforcement learning, specifically the SimClear/MoCo ideas. And so I'll re-explain those ideas in the context of RL. So in RL, typically you have a replay buffer, which is a buffer of past experiences. Your reinforcement learning will look at data in the replay buffer. And then if this is visual data, typically there will be an encoder that encodes that data. And then from there will be a neural network that is the actor and the critic network. And the reinforcement learning algorithms will update the actor and critic network, but typically also backpropagate into the encoder network. And so the reinforcement learning has to do two jobs effectively: learning the actor and the critic reasoning, but also learn the encoder. And so what if after the encoder, we also add a unsupervised loss, specifically the SimClear/MoCo contrastive loss? What can we do then? And how is that done? So in SimClear and MoCo, the idea is that if you have randomly downloaded 2 images and you don't know what's in them, you can still train a neural network to learn more about the world, about the visual world. And the way you do is you say, well, these 2 images were randomly downloaded, so they likely represent different things. And so as your neural network encodes these images, it should end up with encodings that are far apart, typically, because typically there'll be different things in the images. But if you run an encoding that comes twice from the same image, to which you applied some small transformation, like maybe cropping or recoloring or grayscaling it or rotating it in some way, then the neural network should end up with roughly the same encoding because it was the same original image. So if it was originally a dog, it now became grayscale. It's still a dog, it's just a grayscale dog. That's the main idea behind these methods. And so we do the same thing here. We have an input, which in this case tends to be a stack of 3 frames because visual input doesn't show you velocity, and velocity, not in a single frame, and velocity is important for control. So typically you feed in a sequence of 3 frames, then you transform it in a way that keeps invariant the situation, but makes the frames different. In this case, it's cropped in different ways. And those are positive pairs. They need to be embedded close together. And then frames you randomly get from somewhere else need to be embedded far away from that. The loss function that is used for this is typically not just bring it close together in a Euclidean distance, but it's this loss you see at the bottom left. It's the query and the positive key need to be close together in terms of inner product, and this can be a weighted inner product by a matrix W. And then in the denominator, we have alternative keys that come from elsewhere in the data, and they normalize it. And so by them being far away, you actually get the effect that you want here. Whether you weight or not, that's the difference between bilinear and cosine, and weighting it actually helps here. Using an exponentially moving average for the encoder, momentum encoder from the MoCo paper also helps in our case. So we empirically investigated that and used that. The exciting thing is that it actually works. So if you look at these learning curves here, in gray is soft actor critic running from state information. In red is the learning curve when running from visual input. And you see that the red learning curve almost always learns as fast as the gray learning curve, sometimes faster, sometimes a bit slower, which shows that somehow by having the contrastive loss, the encoder is being trained very quickly. And now we can learn as fast as learning from state, even though we only have access to images. And so that's a really exciting result, because before this, there was a factor of 100 gap between the two. Now, you can also compare with other state-of-the-art methods, not just from state versus from images, but what do other state-of-the-art methods do? In this case, curl is our method, contrastive unsupervised pre-training for reinforcement learning, not pre-training, contrastive unsupervised reinforcement learning. And you see that the red curve consistently outperforms previous methods and is almost as good as the gray dashed curve, which is from state. Same thing is true for Atari. So the previous was on Mujoko, which is simulated robotics benchmarks. Then on Atari, similar results. Curl combined with Rainbow, which is the kind of one of the state-of-the-art RL algorithms, a Q-learning type method for Atari. When you add the curl ideas to it, it outperforms prior methods quite consistently. Then there are some environments, as you might have spotted, where the gray curve does outperform the red curve. So you might wonder, well, what's going on? How come it's not always better, not always as good in red as is in gray? Well, we're curious too. Then we said, what if we just run a standard reinforcement learning method? No curl, just D4PG. And we run it for a really, really long time. And that's what you see in green at the bottom. And what happens is it actually saturates at a lower level of performance than the from state learning. What does that mean? It means that somehow, even when training for a very long time, learning from image input cannot match learning from state input. So our hypothesis there then was that maybe the image doesn't have, or even the stack of 3 frames doesn't have enough information. Maybe you need more precise velocity information that's hard to get from a sequence of images. Or maybe you need contact forces information, which is available in the state, but not in the image stack. And so we investigated that, and we ran supervised learning from images to the underlying state and analyzed the error of the supervised learning. And when we trained for a very long time, and what we saw is a very strong correlation there. The higher the error for a supervised learning from image to state, the harder it is to train from images for the reinforcement learning problem. And so at that point, we concluded, look, the environments where this is happening, it's not an issue with that we're not doing good enough representation learning. It's just an issue with just the information not being there in this specific kind of scenario. Okay, now, in some sense, what we did in the curl work is addressing Jan LeCun's kind of challenge that he threw out there kind of 4 years before we did the work. He threw it out there at the NeurIPS keynote, and then 3-4 years later, we addressed it. But there's a whole other part to reinforcement learning that I would say doesn't really fully appear in the LeCun picture so much, though you can think of it as part of it if you want, which is that there is still this notion of providing reward. And you could ask the question, is there any way to do an initial phase of the training without reward? And then only once your robot has been pre-trained on its own, then say now somebody might look at it and provide rewards, or maybe somebody has to write a computer program that can provide rewards, but that's often hard to do. And so that's why you might want to pre-train without the need to provide rewards, then be ready to train when somebody's actively providing rewards much more quickly. And so what is the setting of RL with unsupervised pre-training? The assumption here is that the agent is allowed to train for a very long period with access to the environment, so it can do whatever it wants in the environment, but without access to the ultimate reward. So imagine agent gets dropped in an Atari game, but the score of the game is not available. Or maybe a 2-legged robot can start doing things, but we're not telling it that running is a good thing, that making forward progress is a good thing. It just gets to do things on its own and is supposed to, what I would think of as essentially play. It's supposed to play around in the environment to discover interesting behaviors such that later, when it's asked to solve a task with the reward that then becomes available, it's ready to learn quickly because it has learned basic behaviors already. Maybe it's already learned to run. It doesn't know that that matters, but it's learned it. It learned all kinds of running. Maybe it learned crawling. Maybe in a game, it's learned to deliberately lose it, deliberately win the game. It doesn't know yet what's the right thing to do, but it can pick up a range of skills, hopefully, on its own. The question, of course, then is, how do you incentivize? If you don't give it any reward, how do you incentivize interesting behaviors? And quite a bit of work has happened in that space, actually. So I'm listing some work here on the left. The standard thing is just maximum entropy. You just try to get a policy that maximizes entropy of action given state in every situation. And so you see a lot of random walks effectively that could maybe see interesting things. Then the next one is somewhat of a different version of that. MEPOL is the one that we are most directly building on, which is actually maximizing state entropy very directly rather than just action given state when we look at it. Visor is trying to have the agent learn to predict future things. So what might it see in the future? And so it's exploring and learning to find behaviors where it can make its future a bit more predictable while still having high entropy. Diane is similar. It's something where it tries to essentially find behaviors that are consistent with a latent variable that it samples at the beginning of its rollout. So I'll say, I'm going to sample a latent, and then the rest of my trajectory should be related to this latent that I just sampled. And you can think of that latent as some kind of indexing into skills. DADS is similar, EDL is similar. But if you look at whether they work in a visual domain, and why is that hard? Because it's much higher dimensional. So learning is a lot more difficult. And also the amount of variation you can generate in a visual domain is a lot larger. And so you typically cannot exhaust everything that's possible in a visual domain. You need maybe some slightly better incentives in terms of what you're doing. Most of them don't work in visual domains. Exploration, most of them have some notion of exploration as part of what they do, but not all of them. And then not all of them, but most of them work off policy, which is nice, which means you can reuse old data to keep training your neural network in an RL fashion. APT is the one we'll propose and that I'll talk about. Here's the idea. It's actually quite simple, and in that sense, very surprising. And I suspect also it'll be quite sticky because usually when it's simple and it works, it's natural to just keep using it. When the agent is on its own, effectively playing or doing its unsupervised pre-training, it's optimizing this reward function here. Now remember, I said we're not going to give any rewards, and now I'm telling you, hey, this is the reward function the agent's going to use. But the idea here, and that's shared with all these other approaches that I mentioned, is that you give a reward that is very generic, that does not require you to instrument the environment, require you to give actual feedback. So this reward here is, it's looking at, in an embedding space, Z, it's looking in the replay buffer of past experiences at the k nearest neighbors of the current situation the agent is in. And it's computing the distance to the k nearest neighbors and averaging that. And then, adding an offset and taking the log. But the idea here is that effectively this is measuring where I'm currently at. How different is this from experiences I've generated in the past? So this relates a lot to things you might have heard of before, like exploration bonuses. You get a reward for doing things that are different from your past experiences. But this specific incarnation, we compare with other exploration bonus incarnations in our experiments, happens to work really, really well. And it's also formally tied to a measure of entropy in continuous spaces. And so there is some notion that this measures the entropy of the experiences of the agent. And if you give this as a reward, you'll be optimizing the entropy over states visited by the agent. In this case, not exactly states, but latent space embeddings Z. The latent space can be trained the same way I described before with the curl type loss. So you can have a contrastive loss to discover a good latent space. Here are some learning curves. So Dr. Q is what we build on top of it, some work from NYU. And we use that code. Don't change the base learning of the agent, but then add the pre-training, unsupervised pre-training. In green is our approach, and in red is using count-based bonuses, which is just you count how often you've been somewhere and you reward based on the count being low. And you see that actually this approach I just described is consistently better. In the first 6 is the kind of dense reward tasks. And then if the ultimate task is a sparse reward task, like in the last 6, you can see that this pre-training is critical to get good performance. And it significantly outperforms a more traditional count-based bonus approach. If we look at the overall results here on DeepMind Control Suite, comparing with Dr. Q, which is what we directly use, but then add the active pre-training, curl, which I described earlier, Diane, Meeple, CBB, which are previous methods for encouraging exploration or to do active pre-training, we see that this new method consistently outperforms them. On Atari, we see something similar. The table is probably a little hard to parse, but let me draw your attention to the takeaways. APT, our method, and Visor are the strongest unsupervised pre-training methods, meaning that you get to spend a bunch of time in the game, and then the score gets introduced in the game, and you get 100,000 frames, so 100,000 steps in something in the game to learn to play. We measure performance at the end of that. Visor is a previous approach that achieves a stronger mean. APT achieves a stronger median across the game, so we can look closer here. The bold phase means the winner, and so it's about a half-half split between APT and Visor. What is Visor doing? Visor is doing effectively, it's doing representation learning to predict the things the agent will see in the future, which helps it understand something about the dynamics of the environment it's in. Because if you can predict what is likely to be seen next or next, that means you have an understanding of how the dynamics works. So it's beyond just turning visual input into state, it's also about understanding how states naturally get sequenced. APT and Visor, similar performance. If we look closer, APT tends to do better on the sparse reward games, which in some sense are the harder games. And they'll be interesting to investigate further if we can combine the strength of both. And actually, we've been working on something that tries to bring the strength of both of these together, but we're not fully there yet, even though there are some pretty promising signs. But maybe in the next few months, we'll be able to share something where strength of both gets put together in one approach. Okay, so far we looked in the reinforcement learning setting at learning representations through contrastive learning to effectively address the LeCaque challenge that, learning from visual inputs with just reward signal is just extremely inefficient. By introducing contrastive learning, can learn almost as efficiently from visual input as from state. We looked at effectively letting the agent play is kind of the maybe not analog for kids, but more formally we call it active pre-training for reinforcement learning. Together, they make reinforcement learning a lot more efficient than it would be otherwise. But there's something else that matters too, which is getting the agent to do what you want it to do. And the way this is traditionally done is by designing rewards. So you as a human would say, hey, I downloaded a reinforcement learning algorithm. I want to train this agent. I'm not going to specify a reward function, maybe score in the game, maybe reward based on the quality of the meal a robot makes, or whether you as a car have an accident or not. But you design that, and then it learns against that reward. But actually, often it's very hard to design correctly. So, I mean, for fun, of course, it's great to have these, weird behaviors like the way this robot is running, but it's probably not what you really want. But it's what came out when you run reinforcement learning against the reward functions shown on the right, which rewards for going far in the X direction, the further the better, and penalizes for high action amplitudes or squared amplitudes of actions, and penalizes for the center of gravity, I believe is the center of gravity of the agent to deviate from where it would naturally be, the natural height for it to be. So you don't want it to start crawling, for example. That's what that last term does. But in general, I mean, if it's already hard to define a good reward function for just a running robot, imagine trying to define a reward function for cooking robots. Or there's this famous example of a boat racing game where the designers of the game designed this score in the game, and really it's a game for racing. You see in the little inlay on the top left, you see all the other players are going around the boat racetrack, but the star-shaped icon is the boat we're watching. That's the AI player that was trained with reinforcement learning to maximize the score in the game. And he concluded that doing these repeated circles is the best way to do it, and it is. It hits the right kind of obstacles you get rewards for, and it scores higher ultimate score than what winning the race would give you. And so this is called reward exploitation, where you get a behavior that gets really high reward. It exploits the reward really well, but it's actually not what you want. What's an alternative solution? Well, RL algorithms tend to rely on rewards. That's how they're designed. And maybe there's a way to change that, and I'm definitely open to discussing that, but the approach we took is a little different. We decided to stick with that. We're still going to have rewards, but we're not going to design them by hand. They're going to come from human feedback. So human will give feedback about the performance so far. We'll turn that into a reward function that might not be precise, but it's only temporary, the reward function we use, and we repeat this process. So the way the human will give feedback is by giving preferences between past behaviors. So imagine maybe you're training a dog and you want the dog to sit, and one time it sits, the other time it doesn't sit, then the one where it goes sit is the preferred one, and the one where it didn't sit is the not preferred one. And so the human this way has the ability to interactively guide agents according to the progress they're making. This has a couple of benefits. One benefit is, of course, avoiding reward exploitation, which we talked about. But actually, a more subtle benefit is that it can allow you to teach harder tasks where it's difficult to define a reward function. And what do I mean with that? Isn't it always easy to design a reward function? Couldn't you always say, reward 1 for success, 0 for failure. Well, very often you can do that. 1 for success, 0 for failure is often not too hard to do. But the problem is that existing reinforcement learning algorithms don't learn very well when your reward is so sparse. You only give a 1 for success and 0 for failure, because initially they'll always fail. There will be no signal for improvement. And so the typical practice in reinforcement learning is to design reward functions that measure progress. But designing reward functions that measure progress along the way, that quickly becomes very difficult. And often mistakes happen and the reward exploitation kicks in and so forth. So how do we train agents using preferences? So we need to turn those preferences into a reward, probably, if we want to use a reinforcement learning algorithm. And then we want to make sure that the human doesn't get overly burdened sitting behind a computer choosing between behaviors. So we want this to be very efficient. Okay, so what's the overall framework we've been working with? Step 1, the agent will collect samples via interacting with the environment. Initially, that'll be pretty random, but over time, of course, that'll be pretty good interactions. Step 2, on those interactions achieved in the environment, human preferences are collected. Some were better than other trajectories, and that gets annotated by a human. Then the question, of course, how do you select 2 segments? We use entropy sampling, which means that we actually look at pairs of segments and look at under the hood for the reward function we have learned so far, for which pairs of segments is our reward function most uncertain about which one is better or worse. And those get presented to humans. So you look at a lot of pairs and then look at where's the highest uncertainty, present those pairs to humans. Then we learn a new reward function from these preferences, and I'll say more about that in a moment. And then we optimize the policy using off-policy reinforcement learning, including contrastive learning and so forth, if it's vision-based, to make it maximally efficient. Then we repeat. We go back to step 1. We have a new policy, collects data, and so forth. How do we learn a reward function from preferences? So we have a bunch of rollouts. So a rollout is a sequence of states and actions. And so we look at these segments, and a human will say maybe segment 1 is better than segment 2. Or in this case, segment 2 is better than segment 1. We want to turn that into a reward function that the reinforcement learning algorithm can use. We formulate it as a binary classification problem. This is not something we invented, it's something we use from the literature. So essentially we say, if you have a classification problem, you say, what is the probability that segment 1 is better than segment 0? We're saying it's equal to the exponentiated reward on segment 1 divided by the exponentiated reward on segment 1 plus exponentiated reward on segment 0. So it's just a standard sigmoid type function, standard classifier, but that's the loss function we use. So under this loss function, we want to make the human annotations as likely as possible. And so to do that, to achieve that, then the reward function that we learn should make human preferred segments a higher reward than human less preferred segments. Okay, so it's just a standard loss function. We can optimize neural network to get as high a score on this as possible. Good initial state space coverage is important to make this all work. Otherwise, the human's just sitting there and seeing the robot do uninteresting things all the time. So all the ideas I described in section 3 of this presentation of unsupervised pre-training, we bring them into this. And so I didn't show any videos then, but random behavior would look like what you see on the left. The agent gets dropped, and then it's just kind of doing random actions. And it'd be very hard for humans to score different versions of that. But if you do the APT pre-training that we talked about in the previous section, then you see behaviors like what you see on the right here. And so now, if you see multiple of those segments, it becomes much easier for a human to annotate what might be better, what might be worse. So we're building on the previous 2 sections here to do the RL with human preferences. So here are the benchmark tasks we evaluate on: a few locomotion tasks, a few manipulation tasks, and let's see how this goes. So again, we generate our preferences here from our reward function from preferences over segments, but to avoid having a person sitting there all the time to annotate during all our experiments, we actually have a ground truth reward function that does the annotation automatically for us. That means actually it's quite cheap to get those annotations, but that's just a research thing, a crutch to do research. It's not how it's meant to be used in the future. If you actually have a reward function, you can just use it, but we don't want to rely on human in the loop for all our experiments. So we have a scripted reward function that we rely upon. And we're actually building a benchmark around that for anybody to be able to easily do these kinds of experiments. Okay, and then we can also compare learning with these preferences from that reward function against what we call an oracle, which is reinforcement learning, directly against the ground truth reward function. So we do unsupervised pre-training, then we learn a reward function, we do a bunch of RL, more human feedback, more RL, and repeat. Preference PPO, previous approach that we're comparing with, doesn't do pre-training, has a on policy rather than off policy method. And so we'll see some differences there in performance. And the oracle, the upper bound is agents trained with a true underlying reward. So here are the learning curves. In red is the oracle. And we see indeed, oracle does best on these tasks. But then in green is the approach I described, learning from human preferences. And we see it's almost as sample efficient as the oracle. And previous approaches also learn, but don't, in the time that learning time that we have available here, don't get anywhere near the same level of performance. Green, yellow, and kind of the color between green and yellow are our approach Pebble with different amounts of feedback. So making the red sections here less frequent is an ablation we did. And indeed, if it less frequent feedback, it doesn't do as well, but it still ultimately kind of gets up there in some of those cases. Okay, so we see Pebble is a lot more feedback efficient. You can also ask the question, what if we actually have humans? Does it work? So in this case, we asked the human to provide a feedback. And in 40 queries and less than 5 minutes, they were able to teach 2 different skills to the same robot. And that's a test we want to do, of course. We want to make sure that we're not just always learning the same behavior, because then the human feedback would actually not be incorporated. It'd just be learning something, but not something very deliberate. And so we asked the human to teach it to spin clockwise or counterclockwise. Same here, human was teaching it in one run, was teaching it to wave the left front leg, in the other run, wave the right front leg, and indeed it learns different behaviors. And then we also taught it how to do backflips, which is the kind of classical example people have been looking at in this context, something that's very difficult to design a reward function for, but indeed it works fine with human feedback. Do we avoid the reward exploitation? Can we make it run in a more normal way? Here's a 2-legged walker that's in 2 dimensions, actually, just vertical plane. If you just train it with the standard objective function from DeepMind Control Suite, you get the behavior on the left. It's kind of dragging that right leg every time. With human feedback, you can train it to use both of its legs and do something that really looks like running. So here's a quick summary of the things we covered. We looked at how pre-trained transformers are universal computation engines, meaning that we could train on language and just add a linear input, linear output layer and do well on other tasks like visual recognition or list operations or protein prediction problems. We then looked at contrastive learning in the context of reinforcement learning, which addresses the kind of the cake challenge of not just relying on the cherry on the cake, but using other signal to make reinforcement learning from visual inputs a lot more efficient than it was before. Then it turns out that the reward is often expensive to provide, especially if you have a human in the loop, which we talked about in the end. But if it's expensive to provide, you want to do pre-training. So your agent comes in with a set of skills to do well already, maybe not on the right things, but at least have meaningful behaviors that you can start giving feedback on. In terms of future work, as I look at these, I think there's a lot of future work. Neural architectures, pre-trained transformer models. I think a lot of open questions there. Why does this even work? What happens with larger such models? How can this be more general even than what we've looked at here. For representation learning for RL, I think the vision-based representations, a lot of work has happened there out of my lab, as well as NYU, Montreal, and so forth. I think that's starting to get in really good shape, and there's maybe less future work there on the second direction. The third direction, active pre-training and unsupervised skill discovery, a lot of opportunities there for future work. Even though we're pretty happy with some of the results, it's better than prior state of the art. It's still not great in absolute terms. And so I think there's a lot of opportunity to make this a lot better than it is today. And human in the loop reinforcement learning, again, if you're looking for future research directions for yourself, I think there is a lot of opportunity there. I think it's one of the directions with the best ratio of opportunity divided by number of people working on it. Very few people working on it and a lot of opportunity. So it's a really great place to be, I think, research-wise. Thank you.